Stanford University.
First announcement. I will not be here next week. I have to go to Belgium to give some lecture or other. I will be back, and we will continue this course until the full set of 10 lectures are given. I have no idea where we are now because I get lost sometime around now. But I won't chisel you. You will have the full set of lectures, but I will be gone next week. I think we missed at least one in the very beginning. I can't remember. Was it one or two? One. All right, we're going to miss one next week. They will be made up. I mean, I have many reasons for wanting to make them up. First of all, I don't want to chisel. But second of all, I want to get this full set of lectures out there. So we will continue until they're done. All right, let's talk about some principles. And I want to, I realize I didn't. I was really up to my ears with all kinds of stuff. I have notes from tonight, but I simply wrote them up within the last 3 hours, and I will get them out. If somebody would like to take them and scan them and put them on the website, I would really like that. My scanner takes for hours and hours. It's the slowest scanner in the world. But we'll see. If somebody wants to do that, that's fine with me. In any case, let's just a moment. Let me find my place in here. Looks like that's my place, first page. I appreciate that the last time I did some pretty heavy, intricate mathematics on the blackboard, and I would guess that some fraction of you followed it fractionally. I appreciate that. I understand it. I'm going to go over it again a little bit. You know, you'll be... My teaching policy is to teach until you cry. I've always been like that. But if we are going to take seriously the goal of this course, which is to teach the theoretical minimum necessary to seriously go on to the next level, there's no alternative. I think I've said this before, if I knew a way to do it without the mathematics, I would do it, but I don't. It seems to sort of be a law of nature that nature is expressed through mathematics. I don't know why that's true. Well, I actually do think I do know why it's true, because to the extent that the laws of nature make sense and are exact, they have to be quantified. And how do you quantify things without mathematics and so forth? But it's true that the mathematics gets more and more arcane as you move forward. And this is not because physicists want it this way. It's not because physicists are a bunch of high priests who are trying to hide what they're doing and expressing it in a fancy language that nobody else can understand. It just seems that it is that way. Maybe someday somebody will crack the code. Some young person will see a simplicity in the laws of physics that we don't yet see and be able to express them in a very, very simple equation, x equals 0, and that'll be it. As Feynman pointed out, you can always do that. You can take all of the equations of physics, square them, sum them up, and set it equal to 0, because if the sums of squares is equal to 0, then every term is 0. But that's not helpful.
The only thing I was going to say is, why someone young and not an old fart like Peter did? I think it's time that we oversnap.
I'm with you. I got it. I get it, and I got it. You're right on. Absolutely right. Can we say somebody young in spirit, or we don't even want to say that? Okay, good. Yeah.
You define
defining properties last week. You defined the properties last week, but I didn't hear about the, for me,
The what?
I don't remember the words, uppercase, lowercase,
Oh.
superscript, the subscript. When do you use which one?
Okay, the official rule is a coordinate. This is arbitrary, which is up and which is down. It's as arbitrary as defining your left hand to be this one and your right hand to be this one. Way back when, somebody could have called this right and this left. I'm sorry, I apologize, but you know, you get the point. But which is up and which is down is, of course, arbitrary. There's nothing, it's not that some indices are lighter than air and some indices are heavier than air and float to the bottom. It's just arbitrary. But, all right, so basically the distinction is the coordinates themselves, somewhat arbitrarily, you label with an upstairs index. The differences of coordinates, for example, along a trajectory, you label as dx mu with the index upstairs, Derivatives with respect to x, for example, the derivative of a scalar with respect to x, you think of as having a downstairs index. You think of it as having a downstairs index. And there are many, many other things that also have downstairs indices. Things which transform under Lorentz transformations as coordinates carry upstairs indices. Things which transform as derivatives carry downstairs indices. There's not much difference between them. You go from a thing with upstairs index to downstairs index just by changing the sign of the time component. That's all that's involved here, changing the sign of the time component, but it saves you writing out a lot of work to write that ds by dx mu, now has a downstairs index and an upstairs index. This stands for, what does it stand for? It stands for ds by dx naught, the time component, times dx naught, plus ds by dx1, plus blah, 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 3 terms. And the whole thing is just the change in s in going from one point to a neighboring point, delta s. So here's an example in which it's much more efficient to write ds by dx mu than to write out the whole damn thing. But we need some conventions. We need some rules about when it is we're allowed to sum over the indices without writing summation there. We need some rules. We need to keep track of things carefully. And so the official rule is whenever you see a lower index next to an upper index and they're the same letter, it means sum. That's all. That's the whole rule. There is a deeper geometric meaning to it, but I don't want to go into it now. We'll go into it when we do general relativity. There is a geometric meaning to it. But for us now, the only difference, every vector, let's call it a mu, has both a contravariant life and a covariant life. And the only difference is the component of the vector with downstairs index is the same as with upstairs index, except for the time component where you flip the sign. So it really is just a way. It's just a way of keeping track and not having to write over and over things like t squared or x squared minus t squared, x squared, things like x squared plus y squared plus z squared minus t squared times squared is just equal to x mu x mu. As far as the space components go, lowering the index does nothing, so it really stands for x squared plus y squared plus z squared. And as far as the time component here, the lower time component has its sign changed relative to the upper one, and so it becomes minus t squared. That's the whole point of it. It's just helpful in writing simpler expressions. But if you follow the rules, and you follow the rules of upstairs and downstairs indices rigorously, you will find out that it's very, very easy to write things which are invariant under Lorentz transformations. X squared plus y squared, blah, 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 plus z squared minus t squared is invariant. All right, that doesn't change. It's the same for one observer and another observer. That's what it means to be invariant. And it's equal to x mu, x mu. An upstairs index and downstairs index, when you contract them, which means sum over them like this, that makes a scalar. So there are some nice rules to keep track of. And they're notation. They're notational devices, but very efficient.
If you use just a partial sign as the partial x, is the partial lower index mu?
Yeah.
Is it also
Yeah. Anytime you take a partial derivative, it always carries a lower index.
Does it have a covariant form or covariant form?
Yes, yes, yes. The covariant thing stands for d by dx naught, which means d by dt, d by dx, d by dy, d by dz. This is d by dx mu. When I say it's equal to, I mean the components of this object here are this set of operations. If I want, let's call it just d sub mu, d sub mu. Anytime I have a thing with an index sub mu, I can construct a related thing which is the same collection of objects with an upper index, and all it stands for is minus d by dx naught, d by dx, d by dy, d by dz. So the upstairs thing is the same as the downstairs thing, except the sign of the time component has changed. That's all. So it's not a deep and mysterious thing, and its purpose is just to be able to write things like t squared minus x squared in an efficient way. And since things like t squared minus x squared are the things which are Lorentz invariant, it's a trick for easily recognizing and writing Lorentz invariant things. All right, let's discuss. I want to go back a little bit through the thing we did last time and just sort of sketch it out again, since it was probably kind of tough, and maybe seeing it twice, but not the full thing, might help. But before I do, let's talk about principles. Let's talk about the basic principles. Now, when I say the principles, I mean the principles in the sense of a theoretical physicist today discovers a new phenomenon. Well, it's usually experimental physicists that discover a new phenomenon. But then a theorist wants to make a theory of it. The usual rules. Now, someday the rules might break down, but so far they haven't. The usual rules, for whatever reason, are that the physics should be described, the phenomena should be described by an action principle. There is nothing that we know in nature that is not describable by an action principle. Is this an accident? Probably not. Is this something that's a whim of physicists? Certainly not. We don't know anything that doesn't form this, this pattern. Is it important that, that it has that form? Yes, it is. For example, the derivation of the concept of energy conservation, momentum conservation, all the conservation laws of physics, and especially the relation between conservation laws and symmetries, is entirely through the action principle. If you just write equations, the equations may make perfectly good sense, but if they're not based on an action principle, they will not have energy conservation, momentum conservation, even charge conservation is also an aspect of this. But in particular, let's focus on energy conservation. That is a consequence of the action principle, together with the assumption that things are invariant under changes of the time axis, changes which we call translations of the time variable. So, yeah, writing down physical equations that don't derive from an action principle, we would be giving up the guarantee of energy conservation, momentum conservation. So, as far as we can tell, this is a deep principle. So that's principle number one. We look for an action such that the equations of motion which follow from that action describe the phenomena that is discovered in the laboratory. We look for an action description. That guarantees that it will fall into the category of things with energy conservation and so forth. The action principle means an expression for the action which is minimized by the true solution of the equations of motion. And the equations of motion follow by the Euler-Lagrange equations, the stationary equations for the action. Number two, locality. Locality is basically the principle that if you poke a system at some point of time and space, it has no immediate effect except on things in the immediate vicinity of it. Its direct effect is on things in the immediate vicinity of it. Of course, if I had a string here, violin string, and I poked it over here, it would only affect the neighbor instantaneously. That's locality. But then the neighbor would affect the neighbor down the chain and so forth. And in time, poking it over here would affect it everywhere. But the instantaneous effect, or the short time effect, is local, nearby. And that is guaranteed by requiring a principle of locality in the action, namely that the action is an integral. If it's a particle trajectory that we're talking about, then it's an integral along the trajectory, and it becomes an integral dt. If it's a field theory that we're talking about, a field contained in a volume of space and time, let's paint the space-time region green to represent the existence of a field in there, then the action is an integral not only over time, but also over space, and we can write that integral d4x. The principle of locality, locality says that the thing that we integrate here, the Lagrangian, or the Lagrangian here, this Lagrangian here depends only on the coordinates of the system. If it happens to be a particle, it depends on the positions of the particle, the position components of the particle, and only the time derivatives, x dot. In other words, Lagrangian at this point here depends only on the position at this point and neighboring points, points very nearby. That's the principle that things only affect nearby neighbors either in space or in time. Okay. And for a field theory, it says that the Lagrangian depends on the fields. I'll just call the generic field phi, and the various derivatives. Partial of phi with respect to x mu. Let's just call it phi mu. That means the derivative of phi with respect to x mu. This is enough to guarantee that things only affect their nearest neighbors directly, their near neighbor, and it's the principle of locality that Lagrangians depend only on fields and their first derivatives, not on fields at one point times fields on a very distant point, for example. You could imagine, there's no question, you can imagine a world in which poking something over here has an instantaneous effect over here. In that case, you would not write that the Lagrangian was an integral over something only involving nearest neighbor derivatives, but more complicated kinds of things.
So the question?
Yeah.
So
The last semester of quantum mechanics, we spent some time talking about quantum non-locality.
What's that? Say again?
So the last semester, we spent like a couple of lectures talking about quantum non-locality.
I never talked about quantum non-locality. Never used the word. You guys keep using it. I do not. We talked about entanglement. Entanglement is not non-locality. You cannot affect the thing over here instantly by doing something over here. I tried to make that extremely clear. I tried to make it clear by showing you, for example, how the density matrix of a degree of freedom over here will not change if you try to do something over here. Now, you guys have gotten into your heads some scientific American mentality, some New York Times mentality, that there's something mysterious and non-local about entanglement, and this is not true. You cannot send signals, you cannot affect things at a distance by doing something over here, period. That's not what entanglement does. Entanglement is basically the quantum version, I'm just going to spend one more minute at this, the quantum version of me having two coins in my pocket, a nickel and a dime, closing my eyes, shuffling them up, and giving Alice one of them. I don't tell her which. She doesn't know, I don't know, because I've done it some way. I give Bob the other one, and then send them off home. There is no way that Alice has any direct effect on Bob by looking at her coin. But instantly she knows what Bob has if she looks at hers. All right? It's correlation. It's not effect. It's not effect. Good. All right. Now. Good. Locality is fundamental. Third principle, you require the physics to be Lorentz invariant. In other words, that the rules of the game, the equations of motion, should be the same in every reference frame. That is easy to do. The rule is the Lagrangian should be the same in every reference frame, and that means it should be a scalar. How do you make scalars? You make scalars by following the rules about indices. So the Lagrangian should be a scalar. That's Lorentz invariance. Let's write it down, Lorentz invariance. And the last rule, which we're going to discuss tonight, this is a mysterious rule. This is one that you won't get the first time. Well, you'll get it. Hopefully you'll get what I'm saying, but you won't understand the depth of it and what it really means unless we go through it from various directions, which we'll do. Fourth is another principle of invariance. This is a principle of invariance that the physics doesn't change in going from one frame of reference to another. Incidentally, this includes rotation invariance and so forth. And the fourth rule is a rule called gauge invariance. How many people have heard of gauge invariance? Okay, the majority of you have heard of gauge invariance. How many can tell me what it is? All right, yeah. All right, so tonight we're going to talk. What's that?
You can get away with adding stuff to the Lagrange.
You can get away with adding stuff to the Lagrangian. Certain kinds of stuff. Gauge invariance.
Excuse me, I have a question about number 3.
Yeah.
Lorentz invariance, that has to do with special relativity. What
It
about
does.
general relativity?
Okay, we're not there yet. You're right. You're right. You're right. This is special relativity. So let's suppose that what the experimenter has discovered in the laboratory has nothing to do with gravity. He's quite sure it has nothing to do with gravity. Then these would be the rules.
Right, but the reason I asked that is you said that these are very general principles, but it sounds like...
Yeah. They're very general, but not completely general. You're right. Yes, you're right. Actually, they are very general. They are very general. making the Lagrangian be a scalar has to be slightly modified. It has to be a scalar density. Now, don't worry about it. That's a concept which comes up when we think about curved space-time and so forth. But apart from a very minor change in words, these are the same rules that you would use for general relativity.
But in the case of general relativity, the Lorentz transformation doesn't play a special role.
That's right. That's right. It's a bigger invariance called invariance under arbitrary coordinate transformations. That's correct.
I didn't get the word. Make a scalar what?
Density.
Scalar density.
Yeah. So,
One other question.
but, you know, okay. Yeah.
About item 3, so in the mechanics course way back when, we made Lagrangians, the Lagrangians all had, the terms had dimensions of energy.
Yes.
And so is it correct that that's not a requirement, that as long as they're scalars?
Okay, it is a requirement, but yes. This Lagrangian would have units of an energy. Now, this Lagrangian that goes here would have units of an energy density. And the reason, let's write it this way. Let's write it dt times dx, dy, dz, okay? Now, dx, dy, dz has units of a volume. So there's a factor of a volume here that is not here. Okay? In order to compensate, the Lagrangian of a field theory has to be a energy per unit volume, so that when it's integrated with a volume, it becomes an energy.
Okay, so there is some kind of restriction having to do with dimensions.
Yes. Right. That's true, but you rarely have to worry about it because you tend to work in units where everything is one. So, yeah. Right. Okay. Good. So let's go back through the example we did last time, and I want to work it out quickly on the blackboard again because it is so central, it is so important, and we're going to get to gauge invariance soon, but I first want to go back and just remind you what we learned last time. Try to do it really quickly, and I can do it quickly, I think, if we hold the questions until the end. Okay. Not the end of the class, but the end of the demonstration. All right, so we said, let's just think about the motion of a particle in an electromagnetic field. Right. The first thing we did was introduce a 4-vector, which is the 4-vector vector potential. It's got 4 components. Now, where the hell did it come from? Well, we will see where it comes from, but it is necessary in order to have an action principle which leads to the equations of motion of a charged particle in an electromagnetic field. What are those equations? They're Newton's equations, F equals ma, but with the force given by the Lorentz force law, electric and magnetic forces. You cannot derive that. You can write that down. You know, we can write down, what is the equation? Mass times acceleration is equal to electric charge times electric field plus velocity cross magnetic field. Many of you have seen that before, and there's no vector potential in it. That's correct. You can write the equations without the vector potential, but you cannot express these laws of physics in terms of an action principle without having a vector potential. No way to write it without an action principle. And the action for the charged particle contains 2 terms. The action, I don't want to confuse action and vector potential. I'll just write out the word action. The action is an integral dt. Now, this is a particle. It's not a field theory. It's just a particle in a given electromagnetic field, so it's just an integral dt. Then there's the usual term, which is minus m. No, let's not write that. Let's write just integral The action is integral minus m times d tau. What is d tau? Along the trajectory of the particle, we break the trajectory up into infinitesimal segments and calculate the proper time along each infinitesimal segment, multiply by minus m, and add them all up. This is guaranteed to be a scalar, so it's Lorentz invariant. And then the other term we wrote down was minus e times, it's still an integral, under the integral sign, a mu dx mu. So just to specify exactly what that means, for every little segment here, along that segment, at the position of the segment, right at the position of the segment, there is a vector potential. A vector potential is a field. It depends on space and time. So let's just call it A of x. X stands for x, y, z, and t. A at the position of the segment there times dx mu. And this is a scalar. This is a scalar. If A is a 4-vector and dx mu is a 4-vector, this combination is a scalar. And now we have a potential candidate for an action, and from it we can derive a Lagrangian. Lagrangian, we can write this as the integral of minus m d tau dt. Remember, the Lagrangian always has the form of an integral over time, ordinary time. So d tau is the same as d tau by dt dt. And if you remember what d tau by dt is, you can work it out. It is the square root of 1 minus the velocity squared. 1 minus the square of the velocity. So this is the square root of 1 minus the sums of the squares of the components of the velocity. We worked that out several times. This is the Lagrangian for the particle without the electromagnetic field. And then in the presence of the electromagnetic field is another term, minus E. And now we can write this. The trick is always the same, right? A mu dx mu dt dt. Just a trivial little operation here where I multiplied and divided by dt. But now, what is dx mu by dt? What is dx mu by dt? Has 4 components. What are the 4 components? Well, there's first of all the time component. The time component is the silly thing, dt by dt. So that's 1. And then there are the components of the velocity. The components, ordinary components of velocity. So what this becomes is a sum of 4 terms. Let's write them out. The time component times dt dt plus, let's call it a sub m xm dot. All right, if you didn't get that, I'll show you over here. It's a mu dx mu, and we write dx mu by dt dt. And now let's go through the various terms that are here. First of all is the time component times the time component. That's just a naught, time component, times dt dt. We don't have to write that down. And then the next term is a sub x times dx by dt. And then a sub y dy by dt, and so forth. That's this over here. The index m. It doesn't matter for the space components. For the space components, you can you don't care, right? So you're right. We could put this upstairs, but it doesn't matter for the space components. Space components are the same upstairs and downstairs. All right. So this is vector potential dot the velocity, and that's our Lagrangian times dt. So now we can read out what the Lagrangian is. The Lagrangian for the particle is minus m square root of 1 minus x dot squared. X dot squared means x dot squared plus y dot squared plus z dot squared. This is Lagrangian now. And then minus the electric charge times a naught of x and t plus am of x and t times x dot m. That's the Lagrangian. Oops, let me put the bracket here. From the starting point where we guess a Lagrangian, we work very mechanically. The mechanical rules are straightforward, sometimes a little bit tedious. Sometimes a little bit tedious, and in some deep sense, trivial. They're just mechanically following out the Euler-Lagrange equations for a given Lagrangian. And this is what gets tedious in physics. This is where the tedium comes in, and sometimes there's huge amounts of tedium. I mean, Lagrangians can be very complicated, or Lagrangians can be simple, but the steps necessary to work out and solve the equations of motion can be tedious. So, basic principle, that's the fun part. Working out what the Lagrangian is, that may be fun. And then deducing the consequences of it, that you give to your graduate students. Right. Okay? All right, so let's remember what the consequences of this Lagrangian were. We begin with dl by dx dot. Let's say we pick some component, the mth component, m being 1, 2, or 3, and we compute the L by dx dot. We get something from here that's equal to m, and if you work it out, it's xm dot, the velocity in the mth direction, divided by the square root of 1 minus x dot squared. Okay, that's the L by dx dot. I'm not going to work it out. You can do it. It also happens to be, for future reference, m times dxm by d tau. It also happens to be m times the 4 velocity, oh, sorry, xmm, the mth component of the 4 velocity, m times what we called um.
You need another term. Yeah, there's another term in the Lagrangian. Right?
Yeah, we'll come to it. We'll come to it, right. Right, that's correct. I'm sorry, that's correct. This is an equation which is not finished being written yet. Why isn't it finished being written? Because there's another term which depends on x dot here. So there should be another piece here which is just minus electric charge times am, am of x and t. And let's now, that's it. This is this minus, let's write it correctly. Let's write the equation so that it really is an equation. This minus this happens to be equal to m times um, the 4 vector of velocity, minus e a sub m. Now you should jump up and down and scream like hell that my equation is not consistent. I have upstairs indices and downstairs indices in the same place, but it's okay because it's purely the space component. The space components don't care whether their indices are upstairs or downstairs. So trust me, it's okay. This is the L by dx dot. Now what do we do with the L by dx dot? Lagrange's equations. We differentiate it with respect to time, right? d by dt of dl by dx dot, d by dt of this. Okay. So what do we get? Let's go right down to over here. The left side of the Lagrange equations, the left side of the Euler-Lagrange equations is d by dt, mass d by dt of um, minus e d by dt of the mth component of the vector potential. Right? What is the time derivative of a given component of the vector potential? Now, what do we mean, first of all, by the time derivative? First of all, a may have explicit dependence on time, but it also depends on x. And we're talking about evaluating the vector potential at the position of the particle along the trajectory. So A can vary for two reasons. It can vary because it explicitly depends on time, or it can vary because the position of the particle is varying with time. So there are two contributions to the time derivative. We have to take the time derivative of this thing over here. That's going to be minus e, and there'll be two terms. I'm going to write them down. Derivative of a sub m with respect to t, which I will write derivative with respect to x naught. Same thing. That's one term. And then another term, which is minus. I want to compute the change in a sub m because x is changing. Not because t is changing, but because x is changing with time. And that's the derivative of am with respect to position xn times xn dot, summed over n. There's a term, derivative of am with respect to x times x dot, derivative of am with respect to y times y dot, derivative of am with respect to z times z dot. So this is a sum here. It's a sum over n. That's the left-hand side of the Euler-Lagrange equations. It's not so hard to understand. It has two terms, one coming from the first term in the Lagrangian and the other coming from the second term in the Lagrangian. There's an e here. Do I have the sign right? Yes, I have the sign right, but the electric charge multiplies the whole thing. Minus the electric charge times the whole thing. That's the left side. Now, what about the right side? What's the right side of the Euler-Lagrange equations? Let's just write Euler-Lagrange equations. The right side is the derivative of the Lagrangian with respect to xm. That's it. Okay, so let's go and compute. Where is the Lagrangian? Here's the Lagrangian. What's the derivative of Lagrangian with respect to the x's? How does it depend on the x's? This doesn't depend on x, it only depends on x dot. Only depends on the velocities. Lagrangians depend on positions and velocities. This term only depends on velocities. Forget it. This is a velocity over here, not an x. But a naught and am depend on x. And remember, a naught and am are just fixed things which somebody has told us. Okay, so let's write the right-hand side. Minus derivative of a naught with respect to x. Is that minus? Do I have it right? I think I have it right. Minus e times the derivative of a naught with respect to x. Let me see, I think, yes, that's correct. Derivative of a naught with respect to x. And then from here, I have minus e times the derivative of am, let's call it am, with respect to x. Let's see. No, let's call it, okay. Derivative of an this is xm, derivative of an with respect to xm, axn dot. Let's see where it came from. It came from here. Yeah. All right, I should have gone slower. This is a summation index here. I can change it. I can change its name. We'll call it xn. xn, doesn't matter. All right. On the left-hand side, I'm evaluating the equation of motion for the mth component of position. So there's an m here. It's not a summation index. That's why I didn't use the summation index m over there. I changed variables, changed summation index. All right. So here, I differentiated an with respect to xm, and then just multiplied it by the xn dot, which is already here. It's already there. Just differentiating this whole thing with respect to xm, and that's what you get. All right, now that's a lot of stuff. That's a lot of stuff for a simple equation of motion, but we can combine it together now. Let's combine it together, and it doesn't look so complicated once we combine it together. First of all, the left-hand side, it looks like an acceleration. U is a velocity. It's a 4 velocity, but it's still sort of a velocity. For slow particles, it looks like if particles aren't moving too fast, it's just, sorry, the left-hand side is an acceleration. It's the derivative of a velocity. So it looks pretty much like an acceleration. Let's leave that on the left-hand side. And it looks like ma. It's a little bit different because that's the 4 velocity, not the 3 velocity. But for slow particles, it's approximately the same. So the left-hand side looks like ma. Let's leave it that way for the moment. We're going to come back to it and change it. We're going to come back to it and manipulate it a little bit. Let's put everything else on the right-hand side. What's on the right-hand side will evidently and obviously be the force. All right, ma is equal to the force. So let's put everything on the right-hand side. And I'll temporarily just call this mass times the mth component of acceleration. With a little bit of cheat here about what I mean by acceleration. A little bit of looseness in what I mean by acceleration, but whatever it is, it's the left-hand side of the equation, and that is equal to. Now, on the right-hand side, I'm going to push everything over to the right-hand side, and there's two kinds of terms. One contains a velocity. Yeah, this one and this one contain velocities, and this one do not contain velocities. This is x naught. They do not contain velocities. Let's first take the two terms. Yeah.
I'm just going to say, to make that right-hand side of the equation look more like the left-hand side, would you like to take the e out and change the sign?
No.
And put it in brackets?
Why?
Because then it will look the same as the other.
Sorry, I don't want to write 3 equals 3. I want to write 3 equals something else. But I don't want to write something which on the left-hand side is the same as on the right-hand side. Why would I want to do that? Okay, I'm not sure I'm missing your point. But all right, let's take the pieces which don't depend on the velocity first. So first is this one. When I transpose it to the right-hand side, it's going to have a plus sign. The am by dx naught. Did I get that right? Yeah, the am by dx naught. That's one term that comes from putting this on the right-hand side, and then minus the a naught by dxm. That's a kind of neat little expression. The am by dx naught. The x naught, of course, means time. So this is the am by the time minus the a time by dxm. Nice little symmetry to it. Okay. The second term, where is that? It's the one that involves the velocity, and that is going to be plus the am by dxn. That'll multiply xn dot, but there's another term which also involves xm dot, and that's minus the an by dxm. There's an electric charge, E, and there's an xn dot. So what do I have? I have an mass times acceleration is equal to a first term here, which doesn't involve any velocity. Does not involve a velocity. It's not a velocity-dependent force. It's a force which only depends on position, because position and time in general, but not velocity. And this object has a name. It's called capital E sub m. Again, since it's a space component, it doesn't matter if it's upstairs or downstairs. This is called electric field. Bluntly, that's the electric field. The electric field is a combination of time derivatives of the space component of vector potential and space derivative of time component of the vector potential. That's the notion of an electric field as described in terms of a 4-vector vector potential. What about the other term? Whatever the other term is, it's quite apparent that it multiplies a velocity. Well, I'll tell you exactly what it is now. It is plus v the velocity cross the magnetic field. It's the mth component of v cross b. The mth component of v cross b. Let's check that. Should we check that and see that it really is v cross b? Velocity, v meaning velocity. In other words, x dot. I think I will not check it at the moment. I will leave it for you, but since I haven't yet told you the detailed connection between this object, what is it? Does everybody recognize what mathematical structure dAm by dxn minus dAn by dxm is?
Like the curl.
It's the curl. It's the curl of the vector potential. Let me write down the components of the curl. This is the curl of the vector potential. And the curl of the vector potential is the magnetic field. All right, so it's not obvious at the moment that this is the cross product of a velocity and a magnetic field. But if we recognize that this is the curl, we'll come back to that this is the curl of something, and that the curl of the vector potential is the magnetic field, this is some kind of expression involving the product of components of the magnetic field with components of the velocity. Let's wait a little bit and later on prove that this is v cross b. We have to make some identifications of what b is and so forth. But that's what's going on. That's the Lorentz force law derived from a vector potential. Okay, so this is b. Just to tell you how it works, dA, well, no, let's wait on this. Let's wait on the identification, the detailed identification with the magnetic field. It's pretty clear that it looks something like that. Okay, one last step. This wasn't truly the acceleration. It was not truly the acceleration. It was neither the second derivative with respect to time of x. It was not that. That would be the derivative with respect to time of v. But it's the derivative with respect to time of u. U itself is a derivative with respect to proper time. So we have this funny mixed thing here. D by d ordinary time times u, which is a derivative with respect to proper time. I would like to write everything in terms of proper time. Proper time is a nice relativistic description of time along a trajectory. All right, so let's rewrite this, the left side of it, as m du sub m by d tau, but that's not right. It's not that. We have to multiply this by d tau by dt. The derivative of u with respect to t is the derivative of u with respect to tau times the derivative of tau with respect to t. Derivatives are really ratios. Ratios of differentials of functions with respect to differentials of the independent coordinates. So this left-hand side has an extra d tau by dt. All right, let's follow it through. That's equal to exactly what we have over here. I'm not going to rewrite it. Times x dot n. Now what is x dot n? X dot n is the derivative of x with respect to t. So let's put here dxn by dt. And here we have d tau by dt. What do I want to do with this? Anybody have a suggestion how to neaten this up? I'm going to multiply both sides of the equations by dt d tau to get rid of it on this side. Okay? So we multiply by dt d tau, both sides. Dt d tau here, that will put a dt by d tau here. And it'll put a dt by d tau here. What is this thing? That's the xn by d tau, which is un. Not vn, but un. So we have over here plus e times dam by dxn minus dan by dxm times the 4-vector of velocity. On the left-hand side, we have the derivative of the 4-vector of velocity. On the right-hand side, we have the 4-velocity itself. Now what about dt by d tau? Does that look like it belongs there? Let's write the am by dx naught minus the a naught by dxm. And now let's write dt by d tau as dx naught by d tau. We know that's what it is. D tau. And the x naught by d tau is just the 4th component of the 4-velocity. This is the 4th component of the 4-velocity. It's u naught. So we have, oops, I lost the charge here. There's the charge. We have something that's shaping up in an interesting way. Mass times proper acceleration. So mass times proper acceleration, we could also write this as m d second xm by d tau squared. U is dx by d tau. The u by d tau is a second derivative. This is a form of an acceleration, but it's an acceleration where we're accelerating relative to tau rather than t, the second derivative of the coordinate with respect to tau. So it's called a proper acceleration. And it's a 4-vector. The important thing is this is a 4-vector. On the right-hand side, we have something which involves an electromagnetic field. This is the electric field. This is the magnetic field. And a 4th component and a 4-vector of velocity. I'm going to write this in the form electric charge times F. Let's see if I can get this right. F mu nu u nu. Okay, I'm not quite right yet. Not quite right yet. M. All right. We've seen this object before, I hope. I think we talked about this object before. Oh, one last thing. One last thing. This M index here, is it an upstairs index or a downstairs index? It doesn't really matter. All right, it doesn't really matter. But if we want to rephrase this as a 4-vector equation, we would like to put a mu here and put mu nu. Now that's a properly constructed 4-vector equation, and I will tell you what these things are. This here is the acceleration, the muth component of acceleration. It's a 4-vector. Oh, why am I allowed? Oh, by the way, this, how many equations are here? 3. How many equations are here? 4. Why was I allowed to put the other equation in? Well, if equations are Lorentz invariant, and if the first 3 components of a 4-vector are equal to some other first 3 components, if the first 3 components of a 4-vector are 0, then it's automatically true that the fourth component, in other words, if 3 components of a 4-vector equation are correct, it is automatic that the fourth component is also correct. That's the consequence of Lorentz invariance. And since we ensured Lorentz invariance by requiring that the Lagrangian was Lorentz invariant, we are allowed free to put in the fourth component. Yeah.
Can I ask you about what you just said? Isn't the constant vector like 1, 2, 3, 4? Isn't that Lorentz invariant?
The constant vector, no. What is it? What is a constant vector? No.
NU of x is equals constant 1, 2, 1, 2, 3, 4.
You mean like the numbers 1, 2, and 3, and 4? Numerical values 1, 2, 3, 4?
Is that a 4 vector?
No. No. Let's go back to 3 vectors for a moment. Let's just talk about 3 vectors. Supposing I have, let's even do 2 vectors, 2 component vectors. Is the vector whose components are 1 and 2, what does that mean? That's a vector whose x component is 1 and whose y component is 2. But if looked at from another frame of reference, in fact, let's pick a frame of reference, a particular frame of reference. Let's pick a particular frame of reference that happens to lie along this axis here. All right? In the rotated frame of reference, the x component of this vector is 0. And the y component is what? Square root of 3? 1 plus 2? No, 1, no. Square root of 5. Square root of 5. So no, the thing 1, 2 could be the components of a vector in some particular frame, but it's not a thing which is a 4-vector in that it has the same components in every frame. No thing which has numerical values like this is a 4-vector. The components of a vector transform. The components of a vector transform. So no numerical set of coefficients defines a 4-vector. It's a thing which transforms. Okay, yeah.
In working through here, we try to get rid of dt and express everything in terms of
Right.
except in the electric field where we have the am, the x naught.
No. Okay, that's in here. It's in here. Let's take a look at it. Let's take a look at it. Yeah. Take this term over here. Now, the structure that appears here is a sum. What's it a sum over? It's a sum over nu. Let's write it down exactly. Let's take mu. Let's take the case where mu is equal to m. Mu is a space index. And let's see what this reads. Let's take the case mu equals m. In other words, that mu is a space index and not a time index. And this is m, the mass, times d second xm by d tau squared is equal electric charge. Now, mu is m, so this is Fm, and then nu. Nu can be any one of 4 indices. However, it can't be m. Why can't it be m? It's because F is antisymmetric. We'll come back to that. It can't be m. The diagonal components of F are 0. They're 0. So the next thing it can be is 0. Nu could be 0. And then this would be U0. And then there's the other possibilities. Plus Fm, let's call it N, Un. What is this over here? Fm0 is exactly what's written over here. This is FM0 times U0. So this is already here in this expression here.
Right, I understand.
Yeah.
My question has to do with the fact that dAm dx naught is really just the same as saying dAm dt.
Yes.
Right?
Yes.
And my question was, I thought we were trying to get rid of all the dt's.
No, 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 no. No, not in an expression like this over here. No, no, we weren't trying to get rid of all of the dt's. We were only trying to rewrite. Look, this dt's here. This is dt by d tau. We were trying to write the thing in a form which is manifestly a 4-vector equation. All right? The left-hand side is a 4-vector. It's the derivative. All right. X mu is a 4-vector. dx mu by d tau is a 4-vector because tau is a scalar. And the second derivative is a 4-vector. All right, so this is a 4-vector. And I've just manipulated it around until everything is written in terms of 4-vector notation. This is not the important thing here. The important thing here is that because, all right, let's go through the principles again. I lost the principles, but the principle, first of all, was the principle of locality. The principle of locality comes down to the statement in terms of equations of motion that the equations of motion are differential equations. It says that the force only affects things nearby at the same time or almost the same time. It says that, that's what a differential equation is. It's things are only affected by the force at a given time in the neighborhood of that time. That's differential equations. That's the first statement. Locality tells us that the equation of motion is a differential equation. What could you have that wouldn't be a differential equation? You could have that the acceleration at one time is related to the force at a completely different time. That would be bizarre, but you could have it. The acceleration at one time related to the force at a different time, or even worse, not the acceleration, but the difference of velocity at two completely different times could be equal to the force at some third time. That's exactly the sorts of things that locality forbids. It says the acceleration at a time is equal to the force at that same time. All right, differential equations. Second, Lorentz invariance. The equations can be written as 4-vector equations. That's the important thing here, 4-vector equations, that they're Lorentz invariant.
Would F be considered a rank 2 tensor?
F mu nu is a rank 2 tensor. It's a rank 2 tensor. I'll put up on the blackboard here its components in terms of electric and magnetic fields, and then you can go feed them into here and check that this really is the Lorentz force law. This is the Maxwell tensor, the field tensor. Nu runs this way. Mu runs this way. In other words, this is mu equals 0, 1, 2, 3. Nu equals 0, 1, 2, 3. And we're going to write all 16 components. There really aren't 16 independent components, but all 16 components in a 4x4 array here as a matrix.
One question, is this, the way you're writing it, is that convention standard for a mixed tensor like this, contravariant?
No, no, no. This is actually F mu nu. The only difference now, remember, when you raise an index, if it's a time index, you get a minus sign. If it's a space index, you don't.
So once you've raised it, you don't know which one was first at the bottom, so to speak. Like if I wanted to write that tensor,
There'd be a sign change in some of the components. Yeah. And basically, it's just a question, if you raise the mu index here, if mu is time component, there's a minus sign. If mu is a space component, there isn't. So I'll let you, it's a good exercise to sort out the relationship between the things with the upper and lower indices, but I'm not going to dwell on it now.
I just meant about which are the rows and which are the columns.
Yes, that's why I wrote this down. mu runs this way, nu runs this way. So there's mu and nu. For example, F naught 3. That would be mu equals naught, which would be up at the top here, and nu equals 3.
So suppose I'm given some general tensor, A sub sigma rho,
Right.
one at the bottom, one at the top. How do I know which ones are the rows and which ones are the columns? When one's
You just make it up. I mean, you don't make it up. You just decide on a convention.
That's what I was
Right.
Is there a standard?
No, yeah, this is probably the standard convention, but it's just a way of displaying them. It's just a way of displaying them, and I'm using the convention that nu runs horizontally and mu runs vertically. But you just read them off. Nu equals 3, mu equals 1 would be over here. Right, all right, so I'm just displaying them for you. There's, on the diagonal, they're all 0. It's easy to see that the diagonal elements are 0. It's an antisymmetric tensor. All right, then we have, I think it's minus e sub x, minus e sub y, minus e sub z. These are the components of the electric field. And since it's antisymmetric, that means it's plus e sub x, plus e sub y, plus e sub z. 0, 0, 0. And now the magnetic fields come in a slightly surprising way, but not too surprising. This one is Bz minus By and Bx. And this one is minus Bz, because it's antisymmetric, plus By and minus Bx. Okay. This is the electromagnetic field tensor, and it helps you identify which components of this complex over here, F mu nu, are equal to which components of electric and magnetic field. So what you can do with this is you can now take this and plug it in to this equation and see, let's just see what it says. This is a space-time mixed component. The space-time mixed components are in the upper row here. Time, space. Everything in the upper row has one index, which is time, but then these three things are space components. So that means there's an electric field. This component, a mixed space and time thing, is an electric field. Those are those. And this is a this is a space-space component. M and N are both space, and the space-space components of this tensor are over here. So those are components of the magnetic field. Now, we'll come back to that. But, yeah.
Which form of F mu nu is antisymmetric? Because we have
Either with two upper or two lower. They're both antisymmetric. One upper and one lower, not quite. There's, or maybe, do I take that back? I think by accident it may be antisymmetric. I think all that changes if you have one upper and one lower is the electric fields change sign relative to the magnetic fields, I think. Magnetic fields stay the same, the electric fields change sign. So I think actually they're all antisymmetric. I think.
It's only one,
Is that wrong?
either one row or one column changes sign.
Am I wrong? That doesn't sound right to me, but is it? All right, I don't want to think about it now. For sure, the things with two lower indices or two upper indices are both antisymmetric. Right. And
I think with one upper, one lower, the magnetic part is antisymmetric, the electric part is symmetric.
yeah, I think that sounds right. I think that's right. I don't want to think about it. It'll get me distracted. Right. Okay, so that's the basic setup, but we've never gotten yet to gauge invariance. I went back through what we did last time because I thought it was sufficiently important and so illustrative of the basic principles that to go on beyond it without understanding it would be, you know, a big loss. Okay, now let's go back. Let's go back to the action for the particle along the trajectory, the electromagnetic part of it, and discover the concept of gauge invariance. First of all, what is an invariance? An invariance is a change in a system that doesn't affect anything, or it doesn't that doesn't affect the action. Strictly speaking, it's a change in a system that doesn't affect the equation of motion. For example, I'll give you some examples. F equals ma is an equation of motion. It has exactly the same form if you translate the x-axis, translate the center of the x-axis from one coordinate, from one point to another. That's translation invariance. You can rotate coordinates. Let me give you another example. Let's take a field Lagrangian now, a field theory. The simplest field theory that we wrote down a couple of lectures ago. It had an equation of motion which was d second phi, this was the theory of a scalar field, times dt squared, excuse me, minus d second phi by dx squared, and we can put y squared and z squared in if we want, is equal to 0. I won't put it in. This has a Lagrangian, which is given by d phi, d mu phi, d mu phi. I think it's with a minus sign. Maybe it's minus 1/2 of this. Not important right now. What kind of invariance does this equation of motion have? Well, it has all kinds of invariances, including Lorentz invariance, but it has an additional invariance, which is supposing you just take the field phi and add a constant to it. In other words, supposing I take a field which is a solution of the equation of motion and just add a constant. Everywhere is the same. Does the result satisfy the equation of motion? Well, sure it does. Why? Because the derivatives of a constant are 0. So if I take phi and I know that phi satisfies the equation of motion, and then add a constant, it still satisfies the equation of motion. Why? Because the derivatives of a constant are 0. All right? This is an invariance of the equation of a scalar field, of a very simple scalar field. You can add a constant to phi, and it doesn't affect the equation of motion. You can see it in the action. Here's the action. Supposing I add a constant to phi, what happens to the action? Nothing. The derivative of the constant doesn't contribute. So, if the action is such, or if you have a particular action, and you have a field configuration which minimizes the action, if you add a constant to the field, it will still minimize the action. So adding a constant to a field is a symmetry. It's an odd symmetry. It's the one you're not used to, but it's a symmetry. What happens if I add to the right-hand side of the equation, let's see, I think we used to put in plus, I think we called it plus mu squared phi. That was the equation with an extra term in the Lagrangian, which was minus mu squared over 2 phi squared. Do you remember that? We talked about an equation, a field equation, where we added phi squared to the Lagrangian. This is also a scalar, perfectly legitimate thing to do. Now what happens if we add a constant to the equation? Is it a solution anymore? It is not. There's no change in this term. There's no change in this term. But if we add a constant to phi, this term changes. Look at the action. This term doesn't change if we add a constant to phi, but this one does. Phi squared is not the same as phi plus a constant squared. So with the extra term, this is not a symmetry. This is an example of a symmetry of an equation of motion, which depends on whether the Lagrangian does or doesn't contain this factor. You can do both. Both are perfectly legitimate. Sometimes you have a symmetry, sometimes you don't have a symmetry. Yeah.
In your previous example where you didn't add in that.
Or invariance. I should use the word invariance, yeah.
So what if you said, well, phi add x? Now that satisfies the equation, but it doesn't satisfy the action. See what I'm saying?
You just want to add x to here? Well, x is not a field, it's just a number. I mean, it's just a...
Well, phi is a function.
You want to do it to the action?
Phi is a function of x and t, right?
Phi is a function of x and t.
So if you say, okay, change phi to be phi plus x, which is still a function of x and t.
Oh, I see what you want to do.
So
You want to,
that-
yeah,
that-
phi, you want to say phi goes to phi plus x, let's say.
So that
Yeah.
satisfies that differential equation.
It does.
But it doesn't satisfy it isn't invariant under the action.
First derivative.
Let's see. That does, yes, that does, let's see, that does it doesn't satisfy this equation.
No, forget that part of it.
Yeah, right.
It satisfies that equal to 0.
It does. It does. That's right.
But it doesn't
The
satisfy.
second derivative of this, yes, that's correct. So let's see what happens. So we're getting rid of this, right? And now this thing stands for phi dot squared minus dx phi squared. So if we add, let's see what happens. Okay, I see what happens. You're right, and it's something we're going to come to soon enough. If we add, let's see what happens. We have dx phi plus x squared, okay? That's what you want to do, all right? That doesn't change this term because x, the derivative of x with respect to t is 0. All right, so it changes the action by an amount which contains dx phi squared. Okay, so that gives us dx phi, looks like plus 1 squared.
Why did you say
Yeah.
dx
right,
dt
yeah.
is 0? Why did you say the derivative of x with respect to t is 0?
X and t are independent variables. Yeah. In other words, if a function only depends on x, then it doesn't depend on t. Okay, so that's defined. All right, so what does that do? That adds to the Lagrangian two terms, namely 1, that's 1 squared. All right. Now, adding a constant to a Lagrangian is completely insignificant, does nothing. So we don't have to worry about that. And the other thing is that it adds d phi by dx, actually twice d phi by dx to the Lagrangian. All right. Adding a total derivative to the Lagrangian doesn't change anything. We haven't done that yet. And I'm going to do that in a moment. We're going to see exactly why that's true in one moment. Why adding a total derivative or a derivative to a Lagrangian doesn't change anything. We're going to come to it. That's exactly where I was going, and you sort of stole my thunder by giving this example. Okay. All right, let's go back to the integral of a mu dx mu. We need to keep going in order to get to the concept of gauge invariance, which was the point tonight. Minus e to be exact. All right. Now, consider the following operation on A. We're going to add to A, we're going to add to it the gradient of a scalar, the four-dimensional gradient of a scalar. A is a covariant vector, and ds by dx mu is also a covariant vector. And I'm going to ask whether that changes the equations of motion. Does it change the orbits that the particle will follow? Does it make any change whatever in the dynamics of the particle? Let's add this to A. We're changing A. In other words, we're considering two different A's, an A without the ds by dx mu and an A with it, and ask what the effect on the motion of the particle will be. Well, first of all, it changes the action. Let's see what it does to change the action. It changes the action from the original action to a new thing, which is minus e times the derivative times the integral of a mu dx mu plus ds by dx mu dx mu. It changes the action of the particle. Here's the orbit. The orbit goes from here to here, from point 1 to point 2, and it introduces a new term into the action, which is integral of ds by dx mu. All right? Now, what is the integral of ds by dx mu dx mu? Each one of these little things here represents the incremental change of s along a small little piece of the trajectory. Here's the trajectory broken up into small little pieces. ds by dx mu times dx mu is the change in s in going from one point to another. If we add them all up, it gives us the change in s going from the initial to the final point. All right. So this expression over here, the integral of it, let's put the integral in. Forget the electric charge. It's there, but forget it. We're interested in this quantity over here, ds by dx mu, integrated. That is equal to s evaluated at the endpoint 2 minus s at the endpoint 1. It's just the difference of this function s, this arbitrary function, totally arbitrary function that I added in. It just gives me s at this point minus, or s at this point minus s at that point. Now, does putting in such an s into the vector potential change the dynamics of the particles? And I maintain no, for the following reason. I've changed the action by something which only depends on the endpoints of the trajectory. On the other hand, if I go back to the basic action principle, the action principle states that we search for the minimum action, we wiggle the trajectory, and search for the minimum, for the trajectory of minimum action, but subject to the constraint that we don't move around the endpoints. That's the principle of least action. Don't move the endpoints, but wiggle the trajectory in between. If you want to find the solution of the equations, which goes from point 1 to point 2, hold the point 1 and point 2 fixed and wiggle the trajectory around in between. In wiggling the trajectory around, this term in the action will not change. So if you find a stationary point, a minimum of the action, it will continue to be a minimum of the action when you put in this change of the vector potential. The change of the vector potential, this particular kind of change of the vector potential, not any change of vector potential, but the kind which is adding to the vector potential the gradient of something, the four-dimensional gradient, that has no effect on the motion of the particle. Why? Because it only affects the action through the endpoints, and the rule is vary the trajectory keeping the endpoints fixed.
So S can be any scalar?
S can be any scalar. But this is exactly the operation of putting in a derivative, adding a derivative to the action. Adding a derivative to the action typically doesn't change anything because you can do the integral, putting a derivative into the Lagrangian doesn't change anything because when you integrate it, it just gives you some endpoint contributions. But here it is. All right, so what we've discovered a principle of invariance, that the motion of a particle in an electromagnetic field does not change if you take a mu to a mu plus ds by dx mu. For any s, doesn't matter what s is. This is called gauge invariance. This is the concept of gauge invariance, that the vector potential itself can be changed without any effect on the behavior of the particle, of the charged particle. Certain changes, not every change. Certain changes, those which are ds by dx mu. All right, so adding a ds by dx mu to a vector potential is called a gauge transformation. Where the word gauge came from, it's a historical artifact that had nothing to do with anything. It just became a terminology for some confused reason in the beginning of the 20th century. This was called a gauge transformation, and it stuck, but it doesn't really have anything to do with gauges. Gauges meaning things that measure length. That's what it had to do with. You fail this course if you say gauge transformation. That's one of the main criteria. You say nuclear or gauge. Okay. So, is it really true that the equations of motion don't change if you add to the vector potential such a gradient? To find out, we just go back to the equations of motion. Here they are. Notice that the equations of motion do not directly involve the vector potential. What they involve is the field tensor F mu nu. So any change that we make on the vector potential that doesn't change F mu nu, which means doesn't change the electric and magnetic field, any change that we make on the vector potential that doesn't change these quantities here will not affect the motion of the particle. So the last thing we want to do tonight is show that the electromagnetic field tensor is gauge invariant, that it doesn't change when you add ds by dx mu to the vector potential. That will establish, we know that, it's got to be true. It's got to be true by this argument, but let's prove it directly. All right. What F mu nu is, it's equal to the derivative of the muth component of the vector potential with respect to the coordinate nu minus the other order. Do I have it backwards? I might have it backwards. I always forget. Is F mu nu the A mu by dx nu, or is it the A nu by dx mu? But up to a sign, this is correct. All right. Now supposing we add to A the derivative of S. Okay. So what will it do to this? It will add to it d by dx nu of the shift in A. But what's the shift in A? That's ds by dx mu. And then we subtract off here minus d by dx mu of ds by dx nu. All I've done is shift A by the gradient of a scalar and add the resulting contribution into F mu nu. Now, what is this over here? This is the derivative of a derivative. It's the second partial derivative. This is d by dx mu, d by dx nu of S. But what is this? Same thing. It doesn't matter which order you do the derivatives. This is the fact that partial derivatives commute. That it doesn't matter which order you do the partial derivatives. This is derivative with respect to x nu of derivative with respect to x mu. And this is just the derivatives in the opposite order, but they're the same thing. This is the unimportance of order of differentiation. So this is 0. In other words, F mu nu itself does not change when you make a gauge transformation. So this sort of closes the circle here, and was really the main thing that I wanted to illustrate tonight is that both the action, you can see in the action principle as well as in the equations of motion, this new symmetry, this new invariance with respect to adding a gradient to S. All right, so now you ask, the natural thing to ask is why the hell, if all we were trying to get was equations involving the motion of particles and electromagnetic fields, Why did we bother adding in this vector potential? Particularly if the vector potential isn't unique, if you can change it and it doesn't affect the answers, if you can change it and it doesn't affect the electric and magnetic field, why did we bother? The answer is that there is no way to write an action principle for the motion of a particle that does not involve the vector potential. There is no way that we could have written the action for the particle to go from here to here directly in terms of the electric and magnetic fields. It's only possible to write it by the auxiliary device of the vector potential, and yet the value of the vector potential is not a physically meaningful thing, because if you change it by a gradient, the physics doesn't change.
Is there some utility in making that change, like in solving certain problems or something?
Yes, there's a lot of utility. Sometimes you can add something to the vector potential to make the problem simpler. For example, one of the things you can do is you can always choose an S to set any one of the components of the vector potential equal to 0. That can be very useful. In particular, you can set the time component of the vector potential equal to 0. That itself is also very useful. In fact, the way it usually goes is that by choosing different S's to make the vector potential have this property or that property, you illustrate different properties of the theory. By choosing a gauge, it's called choosing a gauge. Choosing an S that does something to simplify the vector potential may illustrate one property of a theory at the expense of obscuring another property. But by looking at the theory from the point of view of all possible choices of this gauge, then you see all of the properties. So we'll, yeah.
And what about, in the Lorentz invariance case, that corresponds to physics where you're trying to measure something in different situations and compare it.
Say it again.
The Lorentz invariance corresponds to measurements in different reference frames. Does
Yes.
gauge invariance have a similar?
No. No, not really. Not really. That's a good point. Some invariances have obvious physical meaning, and in particular, it has physical meaning because you can imagine two reference frames in the same problem and translating between them. Two physical reference frames, yours and mine. You're an observer, I'm two sets of meter sticks. No, gauge invariance is really not an invariance in the same sense. It's really a redundancy of the description. Many descriptions, all which are basically equivalent to each other. But from a mathematical point of view, it is an invariance. What's new about it? What's new about it is it involves a function of position. If you were talking about rotation of coordinates, you would not want to rotate the coordinates at one place differently than you rotate the coordinates at another place. That wouldn't be an invariance of ordinary physics. To rotate over here this way and rotate over here this way, you rotate by some angle once and only once, and there's no function of position involved. Here there's a function of position, arbitrary function of position, a whole function of position, which is involved in the transformation. That's what's called a gauge transformation. So I don't know why we lost our fundamental principles off the blackboard, but you can now add to locality, Lorentz invariance, action principle, you can add gauge invariance. Gauge invariance is a feature of every known fundamental physics, theory of physics. Electrodynamics, the Standard Model, Yang-Mills theory, gravity, they all have their gauge invariances.
So you showed us that by adding I lost the word, a gradient.
Gradient, no.
By adding a gradient, you don't change the physics.
Right.
Is that essentially the general statement of gauge invariance, that you can add a gradient? Or is there some
Well,
other?
it can get a little more complicated depending on the system. it can be a little more complicated. The Yang-Mills theory, it's a little more complicated than this, but in spirit, it's the same thing. We're going to find a different way to define gauge invariance, a way that, that has some more interesting geometry and the physical picture associated with it. And when we understand that, we'll understand a better way of thinking about it that's more general. Yeah. Yeah.
So you just use it as a construct to highlight different parts of the problem? It's a mathematical construct to highlight different parts of your problem?
Which, the vector potential?
The gauge invariance.
Yeah, well, yes. Yes.
That's really what it is. If it doesn't actually affect the problem overall, you're using it to pinpoint parts of the problem?
Making a gauge transformation can be a useful device for solving a problem, for illustrating a feature of the physics, but it should not change the final answers. Right, and it does not change the final answers.
So we started with a fairly arbitrary vector potential,
Mm-hmm.
and we got electricity and magnetism.
Mm-hmm.
Does that mean other fields or other field theories have a different kind of vector potential?
Mm-hmm.
Because A mu is just,
Mm-hmm.
so what does another kind of vector potential look like? Because it's too early for that.
Excuse me, I'm swallowing my cookie. Let's wait on that. Let's wait on that. Let's wait on that. Typically, they are vectors and they're usually called A. They're almost always called A. They have an index mu to represent the direction of space. So in that sense, they look the same, but they have some additional structure to them associated with other symmetries, and we're not prepared to discuss it now. And we may get to it next week a little bit, but not yet, not yet. Okay. Any other questions?
Yes.
Yes.
You said if we started with the fields, we couldn't have done the action principle. Is that because we're going to have to...
If we started with the field, yes, that's right. There's no known, and I mean, it's not that there's no known. It's an easy to prove theorem, but I won't prove it, that you cannot express the action of a charged particle in a Lorentz invariant way in terms of the electric and magnetic field and position and velocities of the particles. That's a theorem. So if you want to do it in a Lorentz invariant, in a local way, and so forth, and preserve all of these principles, the only choice is to introduce this vector potential, and then you find out that there's this invariance that you can change the vector potential without changing the physics. So it's a very odd and peculiar situation where you have to introduce some auxiliary things into the equations, but the auxiliary things are things which can be changed without affecting the physics. Very remarkable, and it pervades physics. It's all over the place. Do we know why? At the classical level, there's no reason. At the quantum mechanical level, there is a deeper reason, but I would say we've learned that theories of this type have a great deal of beauty, symmetry, simplicity that other kinds of theories don't have. But no, we don't understand why nature always chooses these gauge theories. But it is very pervasive.
So you can't measure A, right?
That's right. You can't measure A, because if you could measure A, you would know what its value is. On the other hand, changing its value doesn't change any physics. And part of making a measurement is physics. You can only measure things by physical processes. If the physical processes are insensitive to the addition of ds dx, you can't measure it. Right? That's absolutely correct. What can you measure about it? Well, you can measure these things, and maybe some other things, but you can only measure those features which are gauge invariant. Okay, so that's a, let's put it this way, it's a totally non-obvious symmetry of electromagnetism, and it's, at this point, it should be mysterious. We'll try to illuminate it maybe next time a little bit.
To try to do a little bit of illumination, I assume there are vector potentials that can be changed in ways that you affect them.
Oh yes, the vector potential, any change that is not of this form will,
Okay.
yeah, any change which is not of that form will be detectable, yeah. Yeah. In particular, there are vector potentials which have absolutely no effect on the motion of particles. If we just take the vector potential itself to be the gradient of a scalar, nothing but the gradient of a scalar, that will have no effect on the motion of the particles. That should be clear to you. If not, think about it. If the vector potential, if the full vector potential is just a derivative of s with respect to x, it will have no effect on the motion of particles. Particles will move in straight lines with no forces on them. Right.
For more, please visit us at stanford.edu.